Okay, thank you. My name is Claudio Carvalho. I work at IBM, and I'm a software engineer, mostly working developing in firmware and kernel, Linux kernel. And Secure Boot is one of the projects that I've worked for the last 5 or 4 years. I've led this effort in the Linux Technology Center at IBM for 4 years. Okay, maybe I should go here. So here. Okay, this is the outline of the presentation. I want to give you an overview of Secure Boot and OpenPOWER systems. I'll try to give some details, implementation, and design from design aspects as well. But we don't have much time, so I'll try to focus on the high-level idea so that we all understand what is Secure Boot and OpenPOWER. And first I will give you a brief introduction on OpenPOWER systems and then Secure Boot. And then I'll talk about the 2 domains we have, the firmware Secure Boot and the OS Secure Boot. I'll use the keyboard here. First, just a disclaimer. So this work doesn't, it represents my view. It doesn't necessarily represent the view of IBM. And all design points disclosed herein are subject to finalization and upstream acceptance. The features described here may not ultimately exist in a final product. And also some trademarks considerations. Okay, OpenPOWER ready systems, or for short, OpenPOWER systems. What is OpenPOWER systems? Well, to understand what is an OpenPOWER system, we need to understand what is the OpenPOWER Foundation. The OpenPOWER Foundation is an open technical membership organization, and here we have the mission of the OpenPOWER Foundation. The OpenPOWER Foundation, it facilitates members to share expertise, investment, and intellectual property. So if you're a member of the OpenPOWER Foundation, you have access to, for example, specification drafts, and also participate in work groups, all related to the Power architecture. And in the OpenPOWER Foundation, we have the OpenPOWER Ready program, and it's a mark to indicate that the product meets the minimum set of characteristics, and also that the product should be interoperable with other OpenPOWER products. So if we have here, if we have an OpenPOWER ready system, I give 4 examples here, 2 Power 8 system and 2 Power 9 system. If we say that one of these systems is an OpenPOWER ready system, it means that it meets all the minimum set of characteristics defined by the OpenPOWER Foundation, and also it is interoperable. The system is also interoperable with other products such as OpenPOWER Ready software, OpenPOWER Ready I/O adapter, OpenPOWER copy. So there are several products under the OpenPOWER Foundation, not only systems. Let's focus on OpenPOWER Ready systems, or just OpenPOWER systems. So I give you 4 examples, as I said, and according to the OpenPOWER compliance and definition document specified by the OpenPOWER Foundation, this system, the firmware of these systems must be a modest derivative of the OP build, and OP build is an open source repository, an open source tool that we use to build the firmware of an OpenPOWER system. And under this OpenPOWER organization here in GitHub, we have other repositories. We have all the firmware components. You can go there and download, take a look at all those firmware components, and you can use the OP build to build all those firmware components. But there are also other software, open source software that is executed in OpenPOWER system. It runs Linux on Power. So we have KVM, and we also have other software, OpenPOWER softwares, open source softwares. One interesting thing of this system is there is also the Secure Boot OpenPOWER Ready, which also a mark. It's something that comes in the front of the machine. It's a sticker. So if the system is also secure, trusted boot and Secure Boot OpenPOWER Ready, it means that it also meets the minimum set of characteristics for Secure Boot and Trusted Boot. All these characteristics are defined by the OpenPOWER Foundation. And I'm going to talk about Secure Boot here, but not about the criteria for these systems to be claimed to be Trusted Boot and Secure Boot OpenPOWER Ready. I'm going to talk about the implementation, the design aspects of the firmware of Secure Boot in these systems. Okay, so what is Secure Boot? Secure Boot is a technology that aims to prevent untrusted code from loading during the platform boot. So when we power on a system, the platform firmware is loaded and it is started to boot the platform for the OS. But the platform firmware, it's not loaded entirely into memory. It's loaded in parts, in pieces, because the platform needs to be initialized, it needs to be booted in parts, not as a whole. So that's why we load it in pieces. And so we have several pieces. The platform firmware is composed of several pieces, and with Secure Boot, we can ensure that only pieces signed with trusted keys will be loaded, will be started. Because if it's not signed with a trusted key, that piece of code, that firmware code will not be executed, and then the platform boot will be aborted at that point. And to do all this verification, Secure Boot uses cryptographic functions. So it uses asymmetric keys, so we sign with the private, and only the public part of that key pair will be able to verify that payload, that blob. But Secure Boot is all about establishing a chain of trust from firmware to operating system. Why is that important? Your operating system, you may have several policies, security policies, robust, sophisticated policies for security, but it doesn't help if you don't trust all the code that was loaded before your OS, because if there is any piece of code that you don't trust, that piece of code can load a malicious code that can compromise your OS, the security of your OS, or it also may compromise the data of your OS, so it may have access to sensitive data. So imagine if you have a MasterCard server and you don't have Secure Boot in that system, so an attacker could have access to sensitive information. And so in Secure Boot, each piece of code is responsible to verify, it will load the next component, the next firmware piece of code, and it is responsible to verify that piece of code. It will load that code and it will verify. And the next code, it's responsible to verify the next one, and the next one is the next one. And if any of these verifications fail, the boot is aborted. Okay, OpenPOWER Secure Boot domains. Here I show a simplified OpenPOWER boot flow. We don't need to understand all this firmware stack here. But if you want to understand it better, you can go to this link here. It describes this boot flow with further details. But as you can see here, the self-boot engine is the first thing that I started in when we power on the system. And as you can see, secure boot from host boot to secure root, we call it as firmware secure boot. And the OS, we call it OS secure boot. Why do we have this separation of these two domains? Because each of these domains has its own requirements, it has its own policies, or it has its own rules for signing an image, verifying an image, and also managing keys. As you can see, we have three components. It's a simplified boot flow. I'm not going to say three because there are much more firmware components here. But we have this from host boot to secure root. We call it firmware secure boot, and then host to OS secure boot. Why don't we verify all these firmware pieces? Why don't we verify the first one, the self-boot engine? No? The self-boot engine, we need to trust on something. It's part of the chain of trust. So we need to have a static root of trust. We need to trust on something. It's in the first piece, we need to trust it. And that's why we put it in a secure memory, because we don't have much secure memory to put all these firmware components. So we put only the first one and start booting from that one piece. It's in a secure memory, so we trust it. But from that point on, every firmware component is verified before execution. Let me watch my time here. Okay. Firmware secure boot. So let's talk about each of these domains. Let's understand it better. Sure. Can you hold the question, please? I can answer. Firmware secure boot overview. Let me try to give you an overview of firmware secure boot. Well, we know that each of these domains needs to have key management. We need to sign the components, the code, each code, and we also need to verify each code. The key, so first we need to set the keys that the platform will trust. We need to set what keys the platform will trust. And only code signed by that key will be accepted, will be executed in the platform. And that's why we store these keys in a secure memory, in a protected memory. But we don't store all the keys as it is. We just store a hash, so we can save some memory. A hash is just 64 bytes, but the full X509 certificate is much more than that. So we store only the hardware public, the hash of the keys we trust, and these keys is the root of trust. From all the other keys, we'll chain back to this hardware public keys hash. I'll explain a little bit more. And we also need to put the code that will be used to verify each firmware component in a protected memory. And we call it verification code, or secure boot container verification code. It's put in a OTP ROM, one-time programmable ROM. So those two pieces are stored in a protected memory. All the rest is installed in an unprotected memory. It's installed in a flash memory, and we use OPBuild to build all the firmware components. As I said, we use OPBuild. You can go to the OpenPOWER Foundation and see the code there. It's open source. And so OPBuild builds all the firmware components, sign them with the keys that you selected, and then it will, as a result, it will build an image that we can flash in this memory here, the PNOR memory. PNOR stands for processor NOR. It's a flash memory. So all the firmware components are stored in this flash NOR, this PNOR. The hardware, the key that we trust is set in manufacturing. So when you buy a system, in manufacturing, we set what is the key and flash it in a secure memory, in a protected memory. And once we enable secure boot, all the firmware components will be verified before execution. And to enable firmware secure boot, we use a hardware setting in the motherboard. So it's a physical thing, but it's platform dependent. For example, it could be a jumper in the motherboard. If the jumper is set, all the firmware components will be verified. And they will be executed only if they were signed with the key we trust. Okay, so let's talk about, I said that we have a verification code that is responsible to verify the secure boot containers. But what is a secure boot container? OP build, it builds secure boot containers. It takes a firmware component, builds a container for that component that is basically a header that wraps the payload, the image itself. And in that container, we have a two-level key hierarchy, which is the firmware public keys. It is used to verify the payload, the image itself, and the hardware keys. We use them. The verification code use these keys to verify the firmware public keys. But who verifies the hardware public keys? So even if I check the signature, if the payload is signed with the firmware public keys, and the firmware public keys are signed with the hardware keys, how do I know if this container is really a trusted container? Well, we calculate a hash of the hardware public keys and check if it matches with the hardware public key hash we have stored in a protected memory. So if this hash matches, we know that that container is trusted, and we can execute it. All the public keys we need to verify the image is in the secure boot container. All the other keys, and the only key we need to store is the hardware public key hash. Okay, so firmware secure boot is, as I said, it's upstream. And here I show only the messages for the ski boot component. And here we can see, let me try to use, it's not going to help. We can see that there are some images, for example, the AMA catalog, CAP, boot kernel. Boot kernel is the ski root. The ski root, this one here. So before loading, before execute, it loads, and before executing these components, it verifies the signature of the component. And then it will execute only if it's trusted, if it was signed with the hardware keys. But up there, you can see that secure mode is not enabled, it's off, because the jumper is not set. And here we can see in the device tree that here is the hardware key hash that is the root of trust for firmware secure boot. So all the containers, if you calculate a hash of the hardware public keys we find in the container, it should match with this hash here. Otherwise, the container is not trusted. Okay, that's firmware secure boot. That's firmware secure boot. With firmware secure boot, we have a chain of trust from self-boot engine to the secure root. Now we need to extend this chain of trust to the host OS. So the secure root needs to verify the host OS image before executing it. OS secure boot is a work in progress at this moment. And I will cover some design points here, and I'll give you some implementation points as well. One interesting thing is that secure root is a kernel. It's a Linux kernel, a recent Linux kernel. And it has embedded the initramfs that runs pdboot. And pdboot is our bootloader. And since it's a Linux kernel, pdboot is a kexec bootloader. So pdboot, we just download or find the Linux from the OS, from the hard disk, and then kexec to that image, Linux and initramfs. Okay, we said that for secure boot, we need to set the keys, we need to sign images, and we also need to verify images. The current design for the OS secure boot is that the OS kernel, so the pdboot, it's our bootloader. You can see all the kernels that pdboot found in the grub.conf or lilo.conf. And all those OS kernels, if you want to execute any of those kernels, the kernel will be signed with the sign file tool that we have in the kernel. The sign file we have in the kernel, it's used to sign kernel modules as well. So we will use the same tool to sign the kernel. In other words, the signature will be appended to the Linux kernel binary. And with that, we can support legacy kernels because we don't change the binary itself. And also, the OS kernel will be verified by the Linux kernel, by the secure root Linux kernel. So the OS, the kernel of the OS will be verified by the kernel of the secure root. And it will be verified by a part of the Linux integrity subsystem named IMA, Integrity Measurement Architecture. IMA is just IMA itself, it just takes measurements when enabled, it just takes measurements of everything that is executed in this system here. But with IMA appraisal and those measurements, so if you run, for example, any binary here in the pdboot, the IMA will track that. It will calculate a hash of that binary and store it in the sysfs. And so that later you can just take a look at what was executed. But with IMA appraisal, it will not just be hashed, what you execute in the user space here. It will also be appraised, so it will also be verified. It will check if that image was signed. And we are extending the Linux kernel here, actually the Linux kernel upstream, to support the appended signature. The signature we are appending to the Linux kernel. So we are extending the IMA to support that kind of signature. And the patches are in process, are being reviewed upstream at this moment. And we are also adding policies for IMA because currently IMA is able just to measure and verify files that we execute but not kernels. So we are extending IMA appraisal to support kernels so that here pdboot, when we try to kexec, it will check, it will verify the kernel that we are trying to kexec. But also key management, we also need to be able to manage the keys, and different from the firmware secure boot, here we have many possibilities. We may have several kernels, and the kernels may be signed with different keys, not necessarily by the same key. And so we need to have a more flexibility to manage these keys. For example, we need to be able to add new keys, to remove keys, to blacklist a key, to blacklist a kernel binary. But we don't need to do that here for firmware secure boot, because when we power on a system, we don't choose, oh, I want to boot this firmware or that firmware. I've never seen that before. So when we power on the system, it will boot on a platform firmware. We don't choose which one. So that's why firmware secure boot is more simple compared to OS secure boot. And the OS secure boot keys, they will be stored in two storages, in the PNOR and also TPM. The PNOR is the memory, flash memory that all these firmware components are stored. So it's not protected. It's not a protected memory. But the TPM, it stands for Trusted Platform Module. It's a cryptographic card that provides also secure memory, protected memory. And it doesn't provide much memory, but we use some of that to secure the keys, to protect the keys. I'll explain more a little bit. And the OS secure boot can be enabled, so this one here, only if the firmware secure boot is also enabled. Otherwise, it doesn't make sense to have secure boot from this point on. We need to have secure boot all through the firmware stack and also the OS. Okay, we have time. So let's talk about a little bit more about these points here. Yeah, let's talk about a little bit more about key management. How OS secure boot works. Okay, the secure boot keys, they are actually stored as secure boot variables, and the secure boot variables are X509 certificates that has the public key inside. And the same idea. We put things there are some things that we need to trust, so those things go in protected memory. The other things goes to unprotected memory. So the critical data we have for OS secure boot is the platform key and also the hash of the other variables. I'll explain more what is the hash. Let's focus on the platform key. The platform key is the root of trust for OS secure boot. So in a certain way, all the other keys needs to chain back to this platform key. And if the platform key is set, it means that the OS secure boot is enabled. If this variable is set, and I can set it from PattyBoot, from the bootloader. And if this variable is set, OS secure boot will be enabled, and all the kernels that we try to load here to kexec to, they will be verified before executed. So the platform key is our root of trust for OS secure boot, and we put it in the protected memory here. The other keys, we put them in the unprotected memory, but we give some protection to those keys, actually integrity protection. We calculate a hash over these keys and put the hash here, because this memory here is protected. So first, before consuming these keys, I need to check if these keys are integrity. First, I need to integrity check these keys. And if the hash of these keys doesn't match the hash that I have here, somebody has tampered with these keys. And I can't trust them, And so I will trust only the platform key, which is our root of trust. And with platform key, we still have our secure boot, so we are good. Okay, we have these other three keys here, what they are used for. The DB, if you want to install a kernel, a OS kernel, and you want to execute it, first you need to add your public key to this DB here. It's a database. You need to add your public key to here because only kernels that can be verified by one of these keys will be executed. But if you have a kernel that was signed by one of these keys here, or that if a kernel that has a hash here in this other variable, the dbx, basically it means that that kernel is blacklisted. You can't not execute it. But how do I add any key to these two variables here? Well, for that I need the kek variable. And the kek variable, it authorizes new entries, new additions to these variables here. So if I have a key here, a public key here, I could sign my key update, and when I try to add, for example, a new key here to the DB, I need to sign that DB entry with one of these keys that I have here in the keg. We have only public keys here, right? And I need to sign that with one of these entries here, and firmware will verify if it was signed with one of those keys, and if so, firmware will add the key to the DB. Same for the other, for the DBX. And in order to add a key to the keg, that key update needs to be signed by the PK, which is our root of trust. So that way we have three-level key hierarchy. So first PK, then keg, and then these two, DB and DBX. So as I said, here in the protected memory we have the hash of these keys. So I need to before ski boot, before these keys are consumed, first I need to check this hash. Before consuming these keys, first I need to integrity check if the hash of these keys match with this one. So, and this, if so, I can use them. And I load them to a cache, a copy here, so that I'm not exposed if anybody changes this memory here, because it's unprotected. And also, before booting the Linux kernel, we write lock this memory here until the next boot, so that anybody from the OS or from the payboot shell are not able to change this data here. And that means if it's write lock at runtime, I cannot process updates at runtime. First, if I want to add a new entry, I can use some runtime services, and then that update will go first up to the update queue, and in the next boot, they will be processed. Because at that point, at boot time, this memory here is write locked. Okay. So just one more thing here. As you see, we have multiple places that we need to update. When we have a key update, we need to update the key here and the hash here. In order to have atomic update, we work with two banks in both memories. And with these two banks and a control bit here, when I have an update here in the queue, I process that update, but I don't update the active bank. For example, let's say that it's bank 0. I don't update it. I update the staging bank, which is bank 1. And if the writes to these banks are okay, then I flip a bit here that in the next boot, the bank 0 will no longer be the active bank, but the bank 1 will be the new active bank. Okay, we're getting to the end here. Challenges. This is how OS Secure Boot works. It's a little bit more complex than firmware Secure Boot. Challenges. We want to reuse the existing user space tools for key management because it involves a lot of effort. We are also trying to use the existing Secure Boot code we have in the kernel. But the most complicated part is to define an interface for the Linux kernel and user space to do the key management, and also user space with the a user space tool to do the key management, add new keys, remove keys, add blacklist a key. And also the interface between the kernel and the Secure Boot, which is firmware. Another thing that is difficult, is a challenge, is safely revoke keys in the kernel. Currently, there is no safe way to do that. It's under discussion. And final considerations, as you saw, it involves a lot of effort. It involves a lot of, it's cross-layer. And firmware Secure Boot is working since Power 8 OpenPOWER system. And OS Secure Boot is in progress. We are discussing part of this design with the Linux upstream community. And we are using the TPM-NV, and it has been shown a good resource for protecting the other keys. And here I just have some references. You can look at these slides. I will upload these slides after this presentation. And unless you don't have any questions, I think that's all I had. Cool.
First, simple one. After Secure Root, the whole OS will be run in a KExec environment. Is that right? I'm not sure.
Yeah?
Yeah. The host OS. Oh, yeah.
It's a Linux kernel, and this Linux kernel has an initramfs with the pettyboot inside the initramfs. And pettyboot is our bootloader. So when we want to boot the host OS, pettyboot will do the discovery of the OS kernels we have in the hard disks. And then it will show all the entries it found. And you can select from one of those, and pettyboot will kexec to the kernel you selected. So it will do a kexec.
When are kernels, when is some kernel added to the forbidden database, to DBX?
That's a good point. As I said, the DBX is the blacklist, and blacklisting keys in the kernel in a safe way is still under discussion. So when the system boots up to pettyboot, at that point I should be able to manage keys from this pettyboot UI or pettyboot console. So I could add new keys to the DB, I could add new keys, blacklist new keys, or I could even set the platform key. So at that point I could do that, but how safely do that? It's still under discussion.
One more. If a vulnerability is found in any step of the firmware Secure Boot, is it game over?
Define vulnerability for me, please.
Some
What kind of
exploitable vulnerability, whatever.
Well, if I'm a vendor and I signed, for example, let's say that I skip bootloads copy, and copy is third party, okay? So skip boot will need to verify the copy image before executing that image. But if the owner of that copy image signed that image as an image that is trusted, I can do nothing else. I can just execute it because I trust that the person that signed that image. So it will be executed. Later, if a vulnerability is found in that image, I can, for example, blacklist that image, but not in firmware, only in OS Secure Boot. If we found a vulnerability here, you need quickly flash a new firmware, update your firmware.
Thanks to our speaker. Now we are ending the session. Now we have a coffee break outside, and we will continue later.